Thank you for joining me. My name is Richard Bowen from Seagate Technology, and today I'm excited to let you know more about our RISC V developments and how they've been helping Seagate continue to fuel the Datasphere. First, I'll tell our RISC V story, then share some details on the microprocessors we've developed, and finally share our vision for how RISC V can play a role in storage at the edge. First, let me tell you a little bit about Seagate. Seagate is a leading provider of data storage solutions and has a range of projects, including hard disk drives, solid-state drives, enterprise storage systems, and consumer storage solutions. We ship more than 400 exabytes annually, storing about 40% of the world's data. Seagate has deep technical expertise across the wide variety of disciplines that it takes to deliver the world's storage. We work with leading storage OEMs, cloud providers, and technology companies to create solutions to challenging engineering problems every day. IT infrastructures are changing rapidly, with massive amounts of data being created and consumed. The industry has seen many transitions in information technology, from mainframes to client server to mobile cloud, and now the edge, where data needs to be stored and acted on with decreased reliance on the cloud. These transitions are driving large increases in the demand for storage capacity, with data creation expected to grow to 175 zettabytes by 2025. We refer to this totality of the storage ecosystem as the Datasphere. Enterprise data is growing faster than other types of data. According to Seagate's Rethink Data report, a survey we commissioned found that enterprise data alone will grow by 42% on average annually over just the next 2 years. To meet these challenges, Seagate is investing in a number of new technologies to fuel the demands of the Datasphere, such as our heat-assisted magnetic recording technology and our Mach2 multi-actuator technology. New technologies like these, however, drive new processing requirements into our products, and RISC V is helping us meet their demands. We also see RISC V playing a key role in driving new innovations in security and domain-specific computation as IT infrastructures continue to transition to the edge. Our RISC V story started about 5 years ago. For many years prior, we had shipped a small internally designed processor implementing a custom ISA. Workloads on this processor were coded in assembly without compiler support for higher-level languages. As a side project, we began investigating creating a compiler for this custom ISA. During that process, we came upon RISC V and decided instead to create a new CPU. Now, this being just a side project, the new design got a little out of hand and soon morphed into an aggressive, out-of-order core that offered a high level of performance compared to many mobile and embedded cores of the day. The humble beginnings of this story really speaks to the power of RISC V. The simplicity and openness of RISC V is what enabled a project like this to get off the ground. The low barrier of entry made it possible to create a proof of concept design that wouldn't have been possible with the barriers of traditional ISAs. With this proof of concept design showing promising performance, we learned of internal HDD processing workloads that were facing scaling challenges going forward. Engaging with those teams, we were able to take the proof of concept design and tailor its performance attributes to their needs. It was soon after that the development effort on the processor was expanded to a larger team to take the core from a proof of concept to a production-capable design with the associated feature set and verification effort that entails. We also began to actively engage the RISC V standards development process at that time. Today, we're in our second generation of development, continuing to enhance our first high-performance core, as well as creating a new area-optimized core for more lightweight and security-critical applications. We also expanded our efforts to the development of a coherent fabric for multi-core deployments. The specific workload for our initial use case is a motion control of the hard disk recording head. By 2026, HDD capacity is expected to reach 50 terabytes, and at that density, the recording media will pack in more than 1 million tracks per inch. To achieve this, The head positioning requires an accuracy of just 2.4 nanometers, an astoundingly small length. To achieve this accuracy, not only does the main servo arm move, as you would see with the visible physical motion, but there are also microactuators at the tip of the arm performing microscopic adjustments. All of this requires an incredibly advanced set of motion control algorithms whose processing requirements increase as the drive capacity grows. This is where the power of RISC V has really shined for us, allowing us to create a microprocessor design that contains many of the real-time features needed by our application at a performance level typically only found in advanced application cores. Now, let me tell you some additional details about our processor design. So today, we're really excited to show you the results of our initial development efforts. This is our first RISC V-enabled HDD storage controller ASIC containing our high-performance RISC V core. With this silicon, we're demonstrating a hard disk drive running the motion control workload on our high-performance core. This is in silicon being demonstrated in our labs now. Both of our processors can be thought of as microarchitectures that enable a family of cores, each with a highly configurable set of features and design parameters. The instantiation in our HDD controller silicon uses the RV32i base ISA, the integer multiply and divide extension, single precision floating point, and the compressed instruction set extension. It supports machine and user modes, along with user mode interrupts. The microarchitecture is a speculative out-of-order design that dispatches 4 instructions per cycle and can issue up to 8 instructions in peak situations. Of course, this much performance requires a high-performance instruction fetch unit, and critical to many of our workloads is a true dual-ported load store unit that can keep memory operations moving at the speed of a wide variety of styles of computation. The load store unit also features large, tightly integrated memories and a multi-way L1 cache to provide options on the reliability of data access latency. Also key to performance in many of our workloads is a decoupled high-performance floating point unit that we'll detail later. The design also features native ECC support on all SRAMs, RISC V debug, and high-speed RISC V and instruction data trace support. This is an overview of the pipeline showing how a typical instruction might flow through the design. First, we have the instruction fetch pipeline that does the address generation, SRAM access, alignment, and ECC correction of the instruction text, feeding a fetch buffer where the variety of predictive features are considered before sending instructions into the decode and dispatch pipeline at a high rate. Instructions are then decoded, register renamed, and work is dispatched into different functional units in the processor. Up until this point, instructions have been flowing speculatively but in order in the pipeline. Next, in the issue stage, execution proceeds out of order as data dependencies are evaluated and resolved. Most of the integer operations are executed and results available for forwarding in a single cycle, while some operations take longer. This diagram details some of the load store unit timing with additional address generation, SRAM access, and result formatting split across 3 cycles. Finally, a retirement queue tracks the completion of operations, handles processing of exceptions, interacts with the RISC V debug module, and generates instruction and data trace controls. It shows some of the additional details of the logical organization of our floating point unit. The design is split into 2 halves, one handling operations destined for the integer register file and the other half destined for the floating point register file. Many of the high-frequency operations are fully pipelined, supporting a high rate of issue, while others, like the square root operation, can process just a single operation at a time over multiple cycles. Here we see some of our performance results compared against 2 other processors advertised as high-performance embedded designs. These are 3 different important internal workloads. You can see that our design outperforms the other cores by 2 to 3 times, a result that holds up with the complete software deployment of our HDD demonstration. This increased performance allows us to continue meeting the processing needs of our motion control system while maintaining computational flexibility for handling new workloads, all while providing the features needed by our real-time control system. This was all enabled by RISC V and its lower barrier to entry to deploying customized computational solutions. Finally, I'll introduce our area optimized core. This design began development more recently in 2019. It too has a highly flexible, configurable microarchitecture and feature set. It enables auxiliary workloads and security applications and targets a small footprint implementation of features over performance. The design has many of the latest RISC V features in development by RISC V task groups, such as the click interrupt controller and enhanced PMP specification. It also focuses on providing optional features targeted at high security applications. This design is a 5-stage single issue in order pipeline. It also has native ECC support, along with RISC V debug and instruction trace. We've talked thus far about the ways RISC V is helping to solve today's challenges in delivering storage technology. Now let's look at where we see RISC V playing a big role in the transition to the edge. Edge devices generate massive amounts of data. Think about cameras or other sensors in smart cities, industrial controls in smart factories, or autonomous vehicles. These devices generate data that needs to be stored, analyzed, and ultimately acted on. But bandwidth for transportation of that data to the cloud can be limited, the connection may be unreliable, or the time to actionable analysis may not be fast enough. This means that edge devices require computational capability to perform analysis near to where the data was generated and functionality to make sure that data and analysis stays secure and trustworthy. This is a huge opportunity for RISC V. Workloads at the edge are numerous and varied, so just as RISC V enabled us to optimize around our motion control workload, RISC V will enable many other domain-specific computation architectures to be created by more people than ever, accelerating innovation in the edge. Beyond computational innovation, RISC V shows strength in the area of security. Built upon a baseline of open, formally proven models, security experts across many companies are collaborating to create best-in-class security solutions required by the edge. This openness is what enables everyone to benefit from each other's decades of experience in security to create something stronger than what any one individual company could have created in isolation. To demonstrate the promise of domain-specific computation, this chart shows an example of an AI inference research project we performed with our high-performance core. The bar on the left is the baseline performance with standard RISC V ISA instructions, and the bar on the right shows the dramatically improved performance we achieved on the same AI inference workload by adding custom tensor instructions to the design. You can learn more about these and other topics in Seagate's 4 other presentations at this year's RISC V Summit. First, our Chief Technology Officer, John Morris, presents a keynote on RISC V accelerating innovation in data storage. Then we have Bruno Masson talking about data on the move, a RISC V opportunity. Bill McSpadden will be providing some details on our approach to pre-silicon verification of our RISC V cores. And finally, Manuel Offenberg discusses the role of RISC V in data trustworthiness at the edge. In summary, I want to emphasize again just how all of the success that we've had was enabled by the power of RISC V. CPU development can definitely be challenging, but RISC V's simplicity and a robust ecosystem of partners made a design as complex as ours achievable. Although Seagate completed much of the design process ourselves, we were glad to have the support of ecosystem partners in areas such as trace and verification infrastructure, which let us focus our efforts on areas which were most valuable and unique to us. The availability of commercial ecosystem partners for all phases of the design process is one of the great things about the RISC V ISA that sets it apart. Another crucial component of RISC V is that many companies, organizations, and individual members who collaborate with each other in creating RISC V standards. There are a large number of technical groups formed covering topics like new ISA extensions, debug infrastructure, security, software development, and market segment special interest groups, and many others. If you are not already, now is really the time to get involved and help us create the future of RISC V. Please visit riscv.org to see how you can get started. Last topic I wanted to touch on is to make sure everyone understands the recent transition from the RISC V Foundation to RISC V International and how that may affect your representation as a member. In order to bring a broader set of voices to the board of directors, RISC V International now has 3 elected seats to represent the strategic class of membership. I'm honored to serve as one of those elected representatives and invite you to reach out to me with your thoughts on the future of RISC V International and what I can do to represent you there. It's important that we all have a voice, so please let me know how I can help. With that, I want to thank you for your time, and I look forward to answering your questions in the chat.